All right, so thank you. Y'all heard, apparently everyone's supposed to give upvotes. I didn't say it, so we're good. And I had this trouble last time. All right, so I am part of gRPC team. However, this is a little bit wider scope than gRPC. gRPC, it's a little bit of how does gRPC fit into the wider story of communicating. And I'll try to be pretty fair to other systems. But I'm going to be a little bit biased. So we're going to go into a rabbit hole. So programming languages, we know them. I'm sort of using this as a jumping off point because we're very familiar with multiple of them typically. And we tend to be a little opinionated about them. So for example, mythical programming language is imperative, strongly typed, dynamically type-checked. And while I'm saying each of these, you're like, oh, yep, I like that. How about this? And you're like, I still don't know. And this is maybe going to be a little bit of a problem. I don't know why that is still down there. It is hiding stuff. Let's see if we just do it again. And it's still about the same, alas. Whatever. So anyways, this time I say it's got lambdas, and I'm like, oh yeah, lambdas. That's where it's at. So that's behind where you can't see. Anyway, so there's these aspects of programming languages and certain things you're like, oh, I really need this, or I don't care about very much like this. But we're quite familiar with them. We can talk about these, and we can throw around these words, and we sort of know what people are talking about. I feel like people are also opinionated about communication systems. But it's a little bit more akin to like Emacs versus Vim. It's a very limited view of sort of the choices that are available. We know some options, and we're sort of just debating between a couple implementations or things like that. It's not sort of on a higher level. And so, like, what are our options? We're like, oh, okay, we've got REST. RPC is the thing these days. Again, we could make something ourselves. And then, yeah, that's it. There's really no options. I'm not sure if y'all realize that. There's basically no options on the market. And of course, I'm jesting. But also, like, let's say that you were going to want, if only my perfect favorite communication system existed. I really wish it was, and what are you choosing between? We're like, oh, request response. Yeah, I know about that. But what's the other things I could be talking about? Client server versus what? Binary versus text. People do tend to be on that one. They know what the other side is, and they know a lot of the advantages and disadvantages. So we've got that going for us. But it seems like there really should be some more. So let's go ahead and start simple and like a pipe. Pretty simple. It's that Unix thing, and you can send on it and receive on it. But there's actually quite a bit to it. Like, I didn't try very hard, and I came up with these things. So if we sort of go into them, it's simplex, means it's only one direction, versus if it was duplex, it'd be both direction. Except for certain OSs like Solaris, if I remember correctly, a pipe is two directions, so we'll just sort of ignore that. But it's basically a single direction. It's reliable, as in it doesn't just drop stuff on the floor whenever it feels like it. It's ordered, so the first byte in will be the first byte out. So if you send 1 and 2, it'll come on the other side as 1 and 2. It happens to be byte-oriented, and this is generally versus message-oriented, although that's a little bit varies system. And that's because it's really working on a bytes. That's the fundamental level it's working. It happens to be streaming. This tends to imply the reliable and ordered. But basically, there's any number of elements, in this case bytes, and then it can terminate. So streams typically have an end, which is sort of a hidden aspect to them. And then it happens to be asynchronous. Whenever you write a byte, you don't know whenever the reader has read the byte. And you tend not to wait for the reader to read. It is flow controlled though, so if the reader isn't reading quickly enough, you're going to have to end up waiting, but that's a little bit different than being synchronous. It happens to be buffered because the kernel will end up buffering some things. This is also related to async. It ends up providing a nice bit of performance, but you also need to sort of account for it, that certain things may not be noticed immediately. Interesting thing is it's anonymous. This means that there's no identity for a pipe. You create one, you're like, this is my favorite, I wish I could tell someone else about it. You can't. It's basically just an FD. And so there's no way to find a pipe. If you could figure out a way to tell someone else about it, there's no way to look them up. It's also serial. If you're sending multiple bytes at a time, and sort of those bytes vary, and there's a couple of other things, but it's really hard to do a read or a write by itself without sort of other synchronization, if you've got multiple readers and multiple writers, because the byte alignment can end up getting off, and it's a little bit hard. If you're doing just single byte reads and writes, you can actually do something more parallel where you could have multiple readers and multiple writers, but it tends not to be all that common. It's more things like make using like -J or things like that. It's a little bit more specialized. But you can go ahead and commonly pair two pipes together. This is where we see a lot of systems do this whenever they're wanting to communicate in both directions. And at this point, it becomes duplex. You can both send and receive at the same time. At the same time, full duplex. So anytime you talk about duplex, you have to ask whether it's half duplex or full duplex. So some systems, it's duplex, but you have to send, and then you have to receive. And if you wanted to send again after you sent, sorry, you need to wait for the receive. And it happens to be full duplex. Both directions of the streams are independent. And it happens to be point-to-point practice. It's very hard to do such a system like this where it's not just one thing on either side. We've got pipe. It's proven, it works really well. It's sort of a little bit low level, but it's very reliable and it works, and we know how to understand it and comprehend it and work with it. It happens to also only be local machine only. There's something related called a FIFO on Unix. You might call it a named pipe. Windows has something else called a named pipe. It's similar, slightly different. It's a little closer to the socket stuff, or Unix domain socket stuff. But basically the only difference is now you have a name for it. So before that thing about it being anonymous, now it is named. There is a file that you can end up opening, and then you can either open it for writing or reading. It happens to be otherwise basically the same as a pipe. It's only one-time use, like a pipe. After it's closed, it's done, and you might as well just delete the file. It doesn't really do much after that point. And then we're coming up onto shared resources. You can tell I'm talking a lot about on a single machine. And let's not ignore the fact that we can just do anything if we have a shared resource. We can communicate however we want, whatever back channel. If we have, let's say, some shared memory, I can set some memory bits, and then someone else can read those memory bits and set some more, and we have that. So you either use just plain shared memory, you might do shared memory plus a shared mutex, across multiple processes or threads or things like that. You can also use files and file locks and something like RDMA for doing that remotely. This sort of thing is actually pretty common in desktop applications or intra-app applications. Whenever an app is sort of trying to talk to itself on a single node, and it's generally associated with high performance. If you can use it and get low performance, but whenever people are going for high performance, this is something they might turn to and try to eke things out. But it also happens to be a bit brittle because you end up sharing quite a bit of state and knowledge, and the things have to coordinate. If any one thing goes wrong, it brings down the entire system and things like that. So it's pretty poorly suited for crossing trust domains when it's some other person is going to be the client. I'm saying client. Some other person's process is going to be interacting with yours, and you don't control that very much. And it's also poorly suited to outgrow the one job it was created for. You try to shove more things in it. Like if you're just going to try to pass more data, that's probably fine. But if you're trying to try to teach it new tricks, it can start growing poorly. There's common patterns, but they tend to be some sort of random application-specific protocol. strongly tailored to whatever that one thing you're doing is. And that sort of makes it a bit too complex to get into, too varied to get into. But I'll just make note here that when scaling over multiple machines, you can still do it, and we still do share resources across multiple machines. But and most of the interaction patterns still hold, but we're going to need some sort of network protocol to do that. But this can be something like as simple as memcached or your database that you end up just having all the pieces of your application accessed directly. That's sort of similar to shared resource in many ways. And then just sort of, I think this is rounding us out. We've got sockets. These are duplex, and they can actually be both for bytes, a stream of bytes, or for messages, depending on its type. It's point-to-point, client-server. We're noticing some terms sort of coming up now. And the server ends up binding to a name or a port, and the client ends up looking up that name in order to find it. And then we'll see this sort of pattern hold in slightly different names and slightly different forms, but it's pretty common. And it happens to be connection-oriented, where you establish the connection, and that has some state to the client and the server, and things are associated with that connection. So for example, Unix domain socket, it supports both bytes and messages. They really behave pretty similar to each other, except whether you're going to do things on byte-based or message-based. And then TCP, which we all basically know, it's going to be bytes. It's a big stream of bytes. And the thing that is cut off at the bottom is a small little note that messages may have a maximum size. That happens a lot in message-based systems. Y'all might think, oh, that TCP thing, we talked about sockets. There's that UDP thing. Yeah, let's not talk about the UDP thing. It's a thing to itself. It's really cool and neat and useful, but it's going to be pretty specialized cases. So this is really a continuation of the socket, but the Unix domain socket is a bit interesting in that it can send more than just bytes or messages. It can actually send file descriptors, these system objects, where you have one and then you send it to another process and then they have it. This is very heavily used for limiting permissions, where you have some privileged process opens a file or something and then hands off the file descriptor to another process. And that means that other process cannot access all the other files, it can just access this one or something like that. But this opens up a sort of question. Now we've got an object, and objects have a lifetime to them. So now we need to manage this lifetime. In this particular case, it tends not to be that bad. The kernel just keeps a reference count. And it turns to be pretty simple because there's no real graph involved. Like a file descriptor doesn't contain another file descriptor. And so it's pretty much just a flat bunch of reference counted objects. There's no graph, there's no cycles, so everything is pretty fine in the world. We went through all these sort of lower level stuff, but we don't tend to use those on a daily basis. It's a little bit too much work. And the first thing to sort of make things easier that sort of came along in, I guess, the 80s was RPC, Remote Procedure Call. So Sun RPC is up there because that was basically the first widely used one. I've used JSON RPC, it did its job pretty well. SOAP is, you could argue, a little bit different, but a lot of people use it for RPC. So I think it's at least fair to put in here. And then gRPC is also RPC. This is a different paradigm. Now we've got request and response messages, and you've got this request-response pair for each RPC. It's still going to be point-to-point client-server, but it's also now connectionless. We are doing things on a per RPC basis as opposed to, we establish a connection and we're going to do a bunch of back and forth communication. But probably the biggest thing that was sort of a big deal was the IDL, or the interface definition language. This is, you go off and you describe your service or protocol or whatever it is, and then it's generally paired with generated code, which allows you to generate that in your language, and you have a nice, clear API. You've got messages and types that you can work with, and you can bundle these together, and you don't have to worry about that anymore. So even back in the Unix domain socket, we had a message-based stream. That's what I said. But that message was just a bunch of bytes. It wasn't actually, it was just it had a particular length, but it was still bytes. In this case now, we are getting something that there's structure involved. You've got two integer fields and a string, and these things start meaning something to you. And then it's a little cut off at the bottom there, but RPC is also synchronous because of this request, and then you're waiting on the response. gRPC was up there. It's a little bit different as well, though, because it also supports a streaming mode. So it's got the client, it's got the request response mode, but you can also just do streaming, which is a different mode. It's going to be full duplex and some things like that, which we talked about with streaming. Also at the bottom, which is, you get to see the right, it's going to be synchronous if you're doing request response. But if you're doing streaming, it can actually be asynchronous. This is a little bit what you tend to make it, it depends on how you use it, how much synchronous or asynchronous it's going to be. But sort of lower level, it can start working a lot more like a pipe at that point. Also, streaming allows pipelining, where this is a little bit of people know serial and they know parallel. It's somewhere a little bit in the middle. Parallel, you're doing multiple things at one time. Serial is you do one thing, you do the next, you do the next. Pipelining allows you to start the second one a little bit before you were done with the first. And typically this is done on the communication itself. So you've got two nodes, and whenever the node, let's say the server, is done processing the work from the first request, the second request is already there waiting for it. And so it can immediately process the second request. It's not going to respond with the first request. The client then says, oh, great, and then it creates the second request and sends it. The client can have already prepared the second request, and that allows you to reduce some latency and some other things. So this sort of goes back to why I made the talk. People aren't necessarily familiar with a lot of these things. And so I talk about, gRPC, it's RPC. Some people, not actually that small of a number of people, were like, okay, well, I've got my service up at the top, and it creates another service. So it's got the create response, and then it's going to return a calculator. And this, at the very bottom there is another service, which is the calculator service. So can you return one service from another service? And actually to do that, the short answer is no. But to do that, you end up needing to pass a reference to that second service. And at the moment you start talking about references, we're now getting into more of an object land. And that means we're going to do remote method invocation. It's basically object-oriented RPC in some ways. So the main thing is that there's an object, it's got some state and methods, but you don't actually send objects. You only send references. And if anyone needs to call any of the methods on, or change the state of the object or anything like that, they've got to send those method calls back to the original object in order to get it to mutate its state. A message, however, is just data, and it's going to be passed by value. You always copy the full message. And it's going to be things like the primitives and structs and like the ints and the strings and things like that. But now we've got a little bit of a problem. So RMI is based on invoking a method on an object, but how do you start? You don't actually have an object to begin with. You need an object to begin with. Pretty much all the systems have some sort of directory service where you can register an object into the directory service, and then the first thing you do as a client is you go find the object that you're looking for. You end up having to cast it to whatever type you're hoping it to be, and then you can start calling methods on it. Casting methods, interfaces. Okay, we need something there to define these things. So there's interfaces that are defined in RMI, and these are just commonly called services. It's various methods, and they've got these parameters. Particular objects will implement particular interfaces or be particular services. And you can end up casting and doing things like that to them. That means that there's a runtime system in place now. in order to check, does this particular reference, this particular object, support these particular methods? That'll vary a little bit in complexity, but many of them do allow you to check, hey, does it support this interface? And we also need a way to maintain object lifetimes, just like we saw before with the Unix domain socket. We're going to have a lot of objects floating around. We're going to need some sort of way to manage them. That's generally reference counting or GC, although that can vary a little bit. And so just to put this into a little bit more concrete, because a lot of people haven't, I think, seen RMI. This was just a simple dbus example I made. I'm a little familiar with Avihi and dbus and stuff, and so I just shoved this in here. But the first line's not too interesting. It's just getting a sort of a global bus. But the second line, the get object, is getting an object by a particular name. It's got some slash path sort of syntax, but it's basically just getting it by its name. The next line is casting it. If this was this is in Python. If this was a statically typed language, that would have been generated code that we would have ended up casting it to a particular concrete type. And then we actually do the actual communication at the very end. And so we were able to call a particular method on that remote object. And in this case, it's actually going to create a new object and return it to us. But that is a very, very common in RMI. Like anytime you start seeing that directory service, that's a good clue that you're in the RMI land. But coming back a little bit is need a way to manage object lifetime. This is a very important part of RMI. It now means that you need to have a full system. It's not just client and server and those two communicate alone. You've got a new full system where you've got references passing back and forth, and think about if you've got a memory leak. It's the system has a memory leak. It is not that process has a memory leak. And you're going to need all the machines are going to need to communicate and figure out how they do this reference counting. When do they release references? How are you going to do garbage collection? Are you even going to bother with circular references or things like that? So how you end up solving this problem is very important to RMI. There's variations. There's simpler versions of it, and there's more complex versions of it. But that's something always to look out for. So sort of going back, I had the list for RPC. This list is for now RMI. It's basically the same list. The only difference is now request response can now be for objects and messages because you can pass the objects around. One interesting thing is sometimes you can interchange those objects and messages. I'm trying to think, I think like Java RMI, it wasn't even clear whenever you called whether you're going to get an object back or a message back. It was sort of up to the server to decide what happened. And that can actually be a very, very hard point whenever you're trying to understand these systems. I strongly prefer whenever those are very clear, there's a clear separation between objects and messages. And then it's also not quite client-server. There's aspects of client-server. You'll commonly see the words client and server, but I think it's a little bit more murky there because it's really like these aren't servers, they're actually objects, and a client can become a server if it's going to pass a listener and stuff. So it's a little bit more murky there. It's still mostly client-server, but I think it's not quite fair to just say it's plain client-server. And then a little bit cut off at the bottom here is sometimes it's also it has network transparency. This was a big thing in some systems, and it's also something to watch out for. I think that this was a big failing point of a lot of the RMI systems is that they were trying to become completely invisible. And whenever you start abstracting away the network at this level, it becomes very hard to figure out how the system is behaving. For example, I said like Java RMI, it was very hard to figure out whether you're dealing with an object or a message. That matters for performance. Also, this network transparency, it matters if you're going to call a getter. You don't want to really be calling a getter from over the network all the time. There's 5 different things. You're going to get one, get the next, get the next, get the next. Generally, whenever you're doing network programming, you're going to do a larger request to get more things all at once because you do have the synchronous nature. So those are things to look out for. Not every RMI system has network transparency, but it's something that very strongly impacts how you end up working with the system. So to give some examples, RMI is still very strong and alive, but mainly on a local system. So Android Binder, which is heavily used on Android phones, it's really an RMI sort of type of system. It can do some other things, but it's got the general pattern I was showing earlier. And I mentioned dbus already. And dbus is how you contact systemd, and a reasonable number of people in here have probably touched systemd at one point to invoke something. But people tend to think about these other ones. DOM and Corba, those definitely come up. DCOM and Corba. Those were the RMI systems that we really think of. And whenever I say RPC, that's actually what a lot of people seem to have in their mind and think about. But Java RMI is in there too. Java RMI is actually not dead. It's, I think, still going with J2EE folks, but it's a little bit more niche. But DCOM and Corba are pretty much dead at this point. One interesting thing, I talked about the local-only RMI with Android Binder and dbus. These tend to be used for transferring system objects again. The reference itself to objects can be considered a secret because you have some system that can enforce that it was actually sent from one process to the other. And so you can pass privileged objects, and in this case, they're actually like application level objects. References, you can pass those references across processes, and this can be also used for security. So, small detour. There's a thing called brokers. So you can have brokered protocols. I'm sort of throwing a lot of them together. Yes. In these cases, you're going to use some sort of intermediary. And so a broker is generally a service that you end up talking to, and then someone else might talk to it. And it's very common for message queues and job queues, a message bus, if you can have watchers and notifications. This is no longer client-server, although you're going to talk generally client-server to the broker itself. But if you're looking at the system, the sort of the wider system, it's no longer client-server. And so, for example, both dbus and pubsub are brokered protocols. dbus is built on top of Unix domain sockets, and pubsub is built off of gRPC. So you're still going to have some sort of a client-server interaction in play, but that's generally an implementation decision, and they can use some proprietary protocol pretty often. But that's still at play. Brokered services, some people just use them for absolutely everything. They have it, and that's the only thing they use. They tend to be well suited, though, for one-way communication, where you want something to be done, you don't care how long it takes, or you don't care where it goes, you just want it to be off your hands. And so a lot of the brokered protocols provide pretty strong guarantees about it will be processed once, or it won't be lost, or those sorts of things. And that's sort of what the broker is providing, is it's going to provide this persistence and make sure it gets done. They're also pretty good for sort of multicasts, where you've got, let's say, an event, you need to send it out lots of places. There's lots of watchers that are interested in that change. You tend to use a sort of broker for those. Exactly how the performance on this operates will vary greatly depending on the implementation and how you're using it, though. I really like brokers. They're great. I think mainly they fall down if you're trying to use them for request response because you just end up paying so much costs. You end up paying so many costs in order to that you're not really gaining much benefit from. So now we're to REST. This is loosely object-oriented. Like there's a resource I see, it has a URI, and that looks like a reference. There's methods that I invoke on that resource. I can pass in these references, I can return them, and sometimes even these references are used for security, where there's a sort of magic, ugly, random number at the end, and someone knows, oh, you must have permission to access this. However, it's a little bit different because there's very few methods involved. And so you tend to add more resources of like you add a slash and then some sort of subpath in order to add more features to a particular resource, where you use a content type or you squirrel stuff away into the request itself in order to sort of add more and more types of operations. There are IDLs for REST, although it's not as essential or I hope it's becoming pretty common, but it's not always used. And interestingly, there's no reference counting, or there's no GC. This means that transient objects that last a very short period of time are very rare. You tend to have a limit in the number of objects you can have per account, or each object costs something in order to force people in order to clean up after themselves. This is also a little bit of a side, but Kubernetes actually uses REST for some of its stuff. It does have a garbage collector. But I'm going to just use this to point out that resources turn out to be a little bit different than objects. If you look at this garbage collector, it's got some configuration and bits to it. And that's because whenever you're dealing with resources, the order of cleaning them up matters. That they get cleaned up soon matters, or maybe it doesn't. And so there's some configuration here that you wouldn't normally see of just a memory-based garbage collector. And there are some additional things on here. Let's see. I think what I'm going to jump forward a little bit and talk about the OO, though, is mainly inside the application. It's the one that's passing these references around. They're not used too much by the system itself. They are used for level 7 routing, although there's some trickery to that. They're also used for caching, although that's mainly for proxies. Clients don't typically cache too much unless you're talking browsers and some things like that. So it's actually pretty interesting that RPCs and REST aren't more different once you start looking at them. And you can do some of the same things that you do in REST in RPCs. But really what turns out is there's a lot of non-functional things as well. There's how does the ecosystem, how good is the implementation? These things can actually have a much bigger impact than the actual protocol itself. So while you're going to be interested in looking at all the functional things, these end up deciding a lot whether make or break. And for example, compatibility was a big problem with Corba. And that's okay. All right, I think we're sort of out of time. That did go longer than I hoped. One or two questions, or
yeah.
Are we done?
Yeah, we should have accounting for the small incident at the beginning. Yeah, let's give it 4 or 5 minutes for questions. Just make sure we keep them brief and not a big storytelling exercise. All right.
Hi. My question is around more specific to gRPC. Mm-hmm. What's the whole idea of deadlines in gRPC? And with context to cloud services using gRPC as a transport mechanism, I'm just trying to ask you, is it a way to kind of like a fencing mechanism or protection mechanism to issue deadlines against RPC requests coming inbound to the service?
Yeah, so deadlines are used a couple different places. They're used on the client itself in order to sort of fail early if it looks like it's not going well. On the server, it can be used to propagate, like if you're just looking at client and server, just that by itself, it's like, not too interesting. But if you start looking at, you've got a system, and pretty much every server turns out to be a client as well. And so being able to propagate the deadline from the original task you were trying to do, which had some time, all the way through the system for all these minute little subtasks, passing that deadline around can be quite helpful so that whenever, let's say it took too long, all those tasks can be cleaned up and you can stop your work. Also, let's say the deadline is too small. You learn that you've got 2 microseconds to do your operation, you scoff and laugh. you can quickly fail the call without having to do a bunch of work.
What do you think about Cup and Proto approach to gRPC?
Yeah, so Captain Proto didn't come in here. It's going to be more object-oriented. It's also got things like the features, feature pipelining. I've not used it heavily, so I don't necessarily know how well it works in practice. I tend to favor simple systems that I can quickly, I don't want to be necessarily fighting the system I'm dealing with. I want to be able to comprehend how the communication is working, and so then the higher level I can understand the pieces and how they're operating. I think it's got some interesting things, but I can't really speak too much on it itself. But I tend to favor simple systems myself.
Is there a quick version of gRPC?
There is a quick version of gRPC on some of the mobile platforms. They are mainly using the CRONet library, which is Chrome's networking stack, sort of turned into a library. And so then you also need you typically have a quick proxy on the server side in order to turn it then back into something more HTTP2 or something like that. It's there. Mobile is where we've seen the most clamoring for it and things like that, yeah.
So that is the time box. Definitely feel free to sync up potentially out in the hall or afterwards. But otherwise, I'll thank Eric for the talk.